This pipeline cathodic protection system works because buried steel naturally surrenders electrons to damp soil. The clever bit here is sacrificing a different metal instead. When an underground steel pipe sits in wet soil, dissolved salts and ground moisture convert the surrounding earth into an active natural electrolyte. Without active corrosion protection, iron atoms continually release electrons into the earth and dissolve into reddish rust, breaching high-pressure steel pipe walls. Engineers alter this natural electrochemical reaction by wiring an auxiliary sacrificial metal object directly to the subterranean steel structure. However, simply attaching a block of active sacrificial metal and burying it beside a long-buried pipeline introduces a severe technical limitation. In dry sand, coarse gravel, or high-resistivity soil environments, the natural galvanic voltage generated between the two metals is far too weak. Because high electrical soil resistance severely restricts electron flow, protective current fails to reach distant bare metal patches along the pipeline wall. These unprotected microscopic gaps continue rusting undetected underground, proving that passive sacrificial anodes alone cannot protect continuous cross-country pipelines. Engineers resolve this limitation by dividing cathodic protection into two distinct technical categories tailored specifically to pipeline length and local soil conditions. For short pipeline segments and isolated utility fittings, sacrificial anodes made of zinc or magnesium deliver reliable, self-powered galvanic protection. For long cross-country transmission lines, operators install an impressed current cathodic protection system that uses an external electrical power source to drive current. A specialized transformer rectifier cabinet converts incoming AC grid power into steady direct current, forcing protective electrons through soil and onto steel. By selecting between passive galvanic anodes and powered impressed current systems, corrosion engineers maintain reliable cathodic protection across all terrain types. The bigger problem is that long, continuous pipelines span hundreds of miles through constantly changing soil chemistries, stray electrical currents, and coating defects. An applied electrical current can easily stray off course into nearby metallic utilities or dissipate uselessly into highly conductive wet clay beds. If localized protective voltage drops below critical standard thresholds, aggressive pitting corrosion rapidly eats deep pinholes through bare steel pipe walls. Conversely, applying excessive electrical voltage causes hydrogen gas bubbles to form at the metal interface, peeling protective epoxy coatings clean off. Maintaining precise millivolt level protection along thousands of miles of hidden underground pipe appeared nearly impossible to monitor and control safely.
Buried pipelines and cathodic protection wiring must not be excavated, disconnected, or tested by viewers. Work requires the pipeline operator, utility location procedures, and qualified corrosion personnel. To control protection precisely, engineers map electrical potential along the entire route using standardized reference electrodes placed directly on the ground surface. A qualified corrosion technician places a copper sulfate reference cell into damp topsoil directly above the subterranean centerline of the pipeline. A high-impedance digital voltmeter connects between the reference electrode and a terminal lead wire attached directly to the buried steel pipe. Industry safety regulations mandate maintaining a minimum negative polarized potential of at least -850 millivolts relative to the reference cell. Holding the steel pipe at this precise negative potential prevents iron atoms from shedding electrons, suppressing chemical oxidation completely across the structure. In impressed current field installations, deep vertical ground beds house durable mixed metal oxide anode arrays installed dozens of feet below the groundwater table. Engineers surround the ground bed with calcined petroleum coke breeze, a highly conductive carbon backfill that significantly reduces electrical contact resistance with surrounding earth. Direct current flows from the positive rectifier terminal into the deep carbon ground bed, passes through damp soil, and enters the steel pipeline outer wall. Because electrons continuously flood into the pipeline exterior, the buried steel acts strictly as a non-corroding cathode throughout its entire operational lifespan. Above-ground test stations placed at regular intervals along the pipeline route house terminal blocks that allow technicians to measure pipe-to-soil voltage rapidly. Field crews perform instant-off current interruptions using synchronized timing relays, eliminating false voltage drop errors caused by electrical resistance in damp soil. In passive galvanic setups, magnesium anodes are packaged inside porous cloth bags filled with a specialized bentonite clay and gypsum backfill mix. This surrounding clay backfill absorbs ground moisture, maintaining consistent low electrical resistance and ensuring reliable sacrificial electron discharge into the pipeline. As the sacrificial magnesium block gradually corrodes away over several decades, it surrenders its own atomic structure to preserve the critical steel pipeline.
Dielectric insulating flange kits are installed at facility tie-ins to prevent protective direct current from leaking into adjacent station grounding systems. Heavy copper bonding jumper cables are thermite welded across mechanical pipe joints to guarantee continuous electrical continuity along multi-segment pipelines.
High durability fusion-bonded epoxy coatings serve as the primary defensive barrier, while the cathodic current protects microscopic coating defects and pinhole flaws. Modern test stations incorporate cellular remote monitoring units that continuously transmit live pipe potential measurements directly to pipeline operator control centers. Engineers dynamically adjust rectifier voltage outputs in response to seasonal groundwater changes, ensuring optimal protective current density is maintained continuously year-round. By pairing robust external factory coatings with precisely regulated impressed direct current and sacrificial anodes, engineers effectively stop subterranean pipeline corrosion permanently. Instead of allowing natural ground moisture to destroy critical steel infrastructure, cathodic systems intentionally direct electrochemical attack onto accessible, easily replaced sacrificial metals. Continuously supplying protective electrons to buried steel transforms a vulnerable, decaying pipeline into an immune, long-lasting cathodic structure beneath the ground. This hidden electrical defense guarantees that critical energy pipelines operate safely beneath our cities, rivers, and fields for generations to come.